Okay, well, we are just halfway, so it's not such a... Well, I mean, we started talking about Wellbore stability and that there is shear fracture and tensile fractures, but we also discussed some other things that about the exam that they didn't need to be recorded, okay? But basically, in order to solve this problem, you will either do it numerically or, fortunately for us, there is an analytical solution which is called the Kirsch solution, and the Kirsch solution allows us to calculate stresses all around the wellbore. And what Kirsch did was actually to solve this equation, but all mathematically with closed form solutions, and so he didn't do any numerical analysis or anything, but he just solved this same equation, but with these conditions. And now we're just going to see the solution for that. It's very important that you remember that this Kirsch solution, it's a little bit limited in its analysis. It has an analytical solution because there are many assumptions in here that you need to make in order to make the problem easier. So first of all, we're assuming a linear elastic solid. Second, you assume that also your rock is homogeneous. And what else? I'm missing one. So linear, it's elastic, it's homogeneous, and also is an isotropic solid. Yes. Those are a lot of assumptions, and we have seen before that rocks are not linear elastic, are not homogeneous, and are not isotropic. So you should take this equation with some, you should be cautious about it, okay? It's an approximation, but in real applications it may be a little different and sometimes a lot different. Yes?
What's the difference between homogeneous and isotropic?
The difference is that if you have something which is homogeneous, that means that its properties as you move in this direction or in that direction, they're all the same. And for example, you could have another material that has like some patches, and as you move from location to location, the properties are not the same. So this one is homogeneous, this one is heterogeneous. And isotropy means that you could have a material like this one that is also isotropic. If you load it in this direction, it responds to the same way that you load it in this direction. And if it is anisotropic, it's not the same as if you load it in one direction or you load it in the other. So one refers to the variations of properties wherever you are with the space. The other one refers to the directionality of the properties. And linear elastic, you remember, it means that strain and stress are linearly proportional. Okay, so you make all of these assumptions and you're going to be able to get to the Kirsch solution that we're going to discuss right now. But before we do that, we need to do something else. As you see, here we have a circle. And if we put it in 3 dimensions, this is going to be a cylinder. It's going to be pretty difficult to write equations in Cartesian rectangular coordinates for a cylinder. So instead of using Cartesian rectangular coordinates, we are going to use, what do you think? What kind of coordinates? Well, polar, you will use polar if you had a sphere. But if we work with a cylinder, we're going to use cylindrical coordinates, right? Okay, so we're going to assume that our wellbore is a perfect cylinder. This is going to be the axis Z, is the only one that's going to survive out of the Cartesian coordinate system. And we're going to have two more axes, or two different axes here. One is going to go perpendicular to Z and perpendicular to the plane of the cylinder, and it's going to be a radius, okay? I'm not going to define it right now, but let's just keep it like that for now. This is an arc from radius. And somewhere in here, inside the three-dimensional space, we're going to have a slice of the cylinder that in 3 dimensions looks more or less like this. So remember that before we were always drawing a cube, right? And we're drawing a cube because we were using a rectangular coordinate system. Now we have to use a cylindrical coordinate system, and we have to define stresses for this cylindrical coordinate system. Okay, so let's start putting stresses on this element in the cylindrical coordinate system. Before I do that, let me tell you that the size of this element, we're going to call the height of this element dz. This is going to be located at the distance. You see, that's why I didn't have to write the r there. I remember there was something. This is going to be r, the distance from the center of the axis to the element. This size is going to be dr. The angle from a predetermined direction to the element is going to be theta, and the angle from here to there is going to be a differential theta. So now we have everything that defines that object. And this is going to be exactly the same as our cube. All right, let's start with the normal stresses. What are the normal stresses? What is going to be the stress perpendicular to that face? How would you call it according to this coordinate system? Sigma, and what would be the subscripts? Sigma RR, which is the stress on the face perpendicular to R and perpendicular to the face, a normal stress, right? What about this one? Sigma ZC, and this is the axial stress. Sigma RR has a name and is a radial stress. Sigma ZC, we already knew sigma ZC, right? But here in this case, we can call it the axial stress. And I'm missing one. And what is the name of sigma theta theta? Probably you remember this from drilling. Well, it has several names, and the names, it depends. You know, if you talk to a mathematician or you talk to a driller, they are all the same thing. It goes either by tangential stress, circumferential stress, or it also goes, the most popular one, by hoop stress. And we're going to refer to it by hoop stress, okay? So sigma theta theta is the normal stress and is the hoop stress. All of these, remember, these are normal stresses. The same as with the cube, we're going to have shear stresses. And for example, here I could have, I'm not going to worry too much here about the directions and of the arrows, if it's positive or negative. Okay, I don't want to get into that with the cylindrical coordinate system because we're not going to use it later on. So I'm just going to draw it here in one direction. I just want to know the name. What is the name of this shear stress? Sigma theta z, and here, opposite to that one, I'm going to have sigma z theta. And what about this one is going to be sigma z r, and here I'm going to have sigma r z, and these one are going to be sigma theta r and sigma r theta. It's the same thing as we have seen before, okay? Remember, there are normal stresses and there are shear stresses. So all of these sigma zr, sigma theta r, and so on, all of these are shear. Okay, so now that we know the cylindrical coordinate system, we're going to be able to use the Kirsch equations to predict what is going to be the state of stress of the rock on the wall of the wellbore or even further away from the wellbore, but at any point. And in order to construct that Kirsch equation, I don't want to give you just the entire equation on just at one time, because it's very long, and I prefer that we know what each of the terms means. So we're going to go term by term, analyzing what they mean, all right? And we're going to start with taking a look at what will be the Kirsch solution for a solid. I'm going to assume for the moment that this is a solid with no pores, okay? We're going to add the porosity later on. But this is just a solid, and around the rock I have stresses in all directions which are the same. And because they are the same in all directions and directionality doesn't really matter, I'm going to call it an isotropic stress. And although I'm drawing here a rectangle, remember that I mean that this is infinitely large. And I'm going to call this one sigma infinity. My objective now is to tell you what is going to be the stress at any part around the wellbore at the distance r and at an angle theta. Before we write any equations, let's try to figure out this just by trying to think about what would happen in this case. First of all, in the wellbore, there is nothing, okay? There is here, we drill away this section of the wellbore, so there is nothing in it. So what is going to be the stress on the wall of the wellbore? Perpendicular to the face. Here, the radial stress around the wellbore. And if there is nothing acting on it, there is no fluid, there is nothing in it. This is just a cavity. This is just a solid. I made a hole and I'm loading it around that. Similar to this, but I'm loading it in all directions. What is going to be the stress on the wall of the wellbore? the radial stress. Let me be more precise. And I want to tell you what is stress as a function of theta, where this is pi and this is 2 pi. The radial stress here at, and let me add one more thing, the radius, I'm going to call it A, at the wall of the wellbore is going to be 0 because there is nothing acting on the wall of the wellbore. So the radial stress sigma RR at the wall of the wellbore is going to be 0. Do you understand why this is 0? Sigma RR is 0 because there is nothing on the wall of the wellbore. But what about sigma theta theta, the hoop stress? You're adding compression from all sides. What do you, is there going to be, first of all, let's go by discarding some solution. Do you expect tension around the wall of the wellbore? You're compressing all of this like that, right? So you expect tension? No. You expect to be 0, the hoop stress at this position? No, not very likely, right? So it's going to be a compression. But let me ask you the following. Do you think the compression is going to be higher at the wall of the wellbore or further away? At the wall of the wellbore, it's exactly the same as that case, right? Because we were taking away what is in the middle. Now what has to take the stress is the rock around it. And what the Kirsch solution tells us is that the value of that stress is going to be 2 times sigma infinity. All around the wellbore, the hoop stress is going to be the same, and it's going to be 2 times the stress in the far field. What that means is that by making a cavity, we have amplified the stress around the wellbore. And the closer you are to the wellbore, the bigger that amplification is. So if I were to measure at any theta, what is the stress, effective stress, as a function of distance r, you will see that in order to compute the stress, at least you need to get at a radius which is equal to the radius of the wellbore, okay? At the distance which is at least a radius of the wellbore. And as soon as you start there, as we said before, the hoop stress is going to be 2 times sigma infinity, and the hoop stress is going to start very high at that point, and as you go further away, it's going to get into the value of sigma infinity, and the radial stress is going to be 0 at the wellbore of the wall, but then it's going to increase as you get further away from the wellbore. And something very important to remember here is that the modification of stress around the wellbore is not going to go forever infinitely far away from the wellbore. Actually, the modification of stress is going to be very limited. And the alteration of stresses, it goes for more or less 3 to 4 radii of the wellbore. You go 3 radii of the wellbore further away from the wall of the wellbore, and the stresses are already what are in the far field, somewhere over here. So the rock is just going to feel the stresses very close to the wellbore. You go a little bit further away, and all these effects of changes of stresses, that magnification of stress, it just gets smaller and smaller. Okay, now that we understand this and we see that it makes sense, let's write the equations. What Kirsch found is that sigma RR, in this case the solution is going to be 1 minus the radius of the wellbore divided the distance from the wellbore squared, both of them, times sigma infinity, and sigma theta theta is going to be 1 plus, and notice the difference in sign, 1 plus the radius of the wellbore divided the distance from the wellbore times sigma infinity. Notice in this equation, when r is equal to a, sigma rr is going to be 0, and sigma theta theta, when r is equal to a, is 2, and 2 times sigma infinity is the value of the stress. Yes?
Can you explain again why sigma RR is 0?
Here?
Yeah.
So let's make a zoom out of this section. We're going to see later on that this is a solid. This is a solid, and we're going to relax this assumption, but at this point there is no fluid inside. If we had a fluid, like you may think of this as a pipe. If there's fluid inside the pipe, you're going to have a pressure, but there is nothing. There's no chance, there's no possibility of having a radial stress. So in this case, the radial stress is equal to 0. There is no such thing like that. Two more things, guys. Just give me 1 minute to finish this concept. Something very important to remember here is what I told you about the stress amplification, that sigma theta theta at r equal to a divided sigma infinity is equal to 2. That's something that we call stress magnification or stress intensification. And second is that notice that sigma theta theta divided sigma RR is equal to what? At the wall of the wellbore. Sigma theta theta divided by sigma RR is infinity. And that means that this rock cannot resist, or it can resist this stress only if it's cemented. You remember that uncemented materials cannot have any stress anisotropy if they don't have any effective stress support. And this is the reason why you cannot make wellbores in dry sand. Because at the wall of the wellbore you get to this condition in which the rock just fails. Okay? All right. We'll continue with this on Wednesday. And remember that I have here your exams. Okay? See you on Wednesday. No. Tell me your last.